Hello, I'm Juliette Drupt from the Cosmer Lab, Université de Toulon, and I'm going to present our work on the validity of the catenary model for moving submarine cables with negative buoyancy. In underwater robotics, tethers can provide real-time communication and energy supply to remotely operated vehicles. Tether management strategies or vehicle localization may require a tether shape estimation, which may rely on a cable model. On the one hand, the cable can be constrained to a simple piecewise linear model by the addition of buoys and ballasts. On the other hand, hydrodynamic models describe the general case of any cable but are not suitable on line. Alternatively, the cable can be modeled by a catenary. A catenary model is a parametric planar curve defined in a vertical plane. It gives the shape of a quasi-static, homogeneous hanging cable with fixed length and fixed ends, only subject to its own weight, and, optionally, to the Archimedes buoyancy. It's an alternative to a complete physical model, which is sometimes used in aerial robotics. However, how reliable is it for underwater cables with moving ends? This work focuses on answering this question experimentally by the motion tracking of two different underwater weighted cables. The experiments are conducted in a pool. Motion tracking markers are placed on the cable. One of the cable ends is fixed, and the other is tied to a stick to be moved by an operator. Two cables are tested, a metal chain and a light, thin rope, denoted respectively cable 1 and cable 2. The mobile end is moved in various directions with slow and rapid motion to figure out the limits of the model. 3 catenary properties are evaluated, being planar, in a vertical plane, and fitted in 2D catenary curve in this plane. Given a set of cable points pi, a plane P is computed by minimizing point-plane distance. The residual of this optimization is denoted EP, and the angle of plane P and the vertical is denoted alpha. In a second term, the closest inclined catenary curve in plane P is estimated by minimizing the distance to the projection of all 3D points in P. The residual is denoted EC. Here is a video of the experimental results. The values computed for alpha, EP, and EC are displayed on the left. The 3D points and estimation when enough points were tracked are displayed on the right. The red circles denote the 3D points and the blue crosses their projection in plane P. The inclined catenary curve is in orange. The number n of tracked points is indicated below the figure. The subsequences were selected to include various kinds of movements. You can see now the results of the tracking of cable 1. As you can see, the tracked points are very close to the estimated orange inclined catenary curve. In addition, plane P seems almost vertical. Here are the same results for cable 2. You can notice that the output of the plane fitting oscillates a lot at the beginning of the sequence, but gets more stable after t equals 16 seconds. This is due to two main things. First, the points which are visible change rapidly between 14 and 16 seconds, and second, most tracked points belong to the same side of the cable's curve and are almost aligned on the 3D line in this time interval. The results are much better after t equals 16 seconds, with more stable tracked points placed on both cable sides. Plane fitting residual EP, plane angle alpha, and inclined catenary fitting residual EC are computed for each cable along the full sequence. The smaller EP, the more planar the cable, the smaller alpha, the more vertical the plane, and the smaller EC, the more inclined catenary-like cable. One can see that cable 1 stays almost planar in the general case, that this plane is very close to the vertical, and that the cable is very well fitted by an inclined catenary curve. Cable 2 stays almost planar too, and is quite well fitted by an inclined catenary, but the cable's plane is not vertical in the general case. In conclusion, a heavy enough cable can be well described by a catenary, even with moving ends, but this model is not valid for lighter cables. This work demonstrated experimentally that an inclined catenary model can provide a good approximation of the shape of such lighter cables, what is promising for future underwater cable shape estimation. In addition, the inclined catenary model can also express a vertical catenary in an inclined frame, like the one of a rolling tethered robot. Avoiding abrupt changes of directions will also help conforming into the model. Finally, the inclined catenary model might be used for underwater cable shape estimation purposes. Thank you for your attention.